Today we are finding the torque acting on an electric dipole and work done in rotating an electric dipole in a uniform electric field. For that, consider an electric dipole minus q, this is plus q. This dipole is placed in a uniform electric field whose intensity is E. Effective length of the electric dipole is 2L. Now the forces acting on the electric dipole are plus QE and minus QE. Due to these two forces, the dipole will rotate in the electric field, means it comes into rotational motion. Therefore, the torque will be acting on it. For finding the torque, the electric dipole is rotating in the electric field. The angle between the electric dipole moment P and electric field intensity is theta. Its alternate interior angle is this one, that is theta. Now for finding the torque, before that the net force acting on the electric dipole will be equal to plus QE and minus QE, that will be equal to 0. For torque, we know the torque will be equal to force into perpendicular distance between forces. So therefore torque will be equal to F into AC. AC is the perpendicular distance between the forces. So torque will be equal to QE into AC. For AC, we are considering the right angle triangle ABC. In that, sin theta will be equal to perpendicular upon hypotenuse, that is AC upon AB. So sin theta will be equal to AC upon 2L, because AB is equal to 2L. So therefore AC will be equal to 2L sin theta. This value is substituted in equation 1. So torque will be equal to QE into 2L sin theta. But you know 2QL is equal to P. So therefore torque will be equal to P sin theta. It can be written into the vector form because torque is vector quantity. Electric dipole moment is also vector quantity, and intensity of electric field is also vector quantity. So torque will be equal to vector vector P cross vector E, that is cross product of P and E will be equal to torque. Conditions for the torque: if theta will be equal to 0 or 180 degree, then torque will be equal to 0, because sin 0 and sin 180 is equal to 0. If theta will be equal to 90 degree, then torque will be maximum and it will be equal to PE, because sin 90 is equal to 1. Then for finding the work, as you know, work will be equal to force into displacement. This is for the linear motion, but here the motion of the dipole is rotational. Therefore the force is replaced by torque and displacement is replaced by angular displacement. Let small angular displacement is equal to d theta. So therefore the small work is dw, that is equal to torque into d theta. But torque is equal to P sin theta. Therefore dw will be equal to P sin theta into d theta. This is the small work done in rotating the dipole by a small angle d theta. For finding the total work, we have to integrate both sides. So integral of dw, that is integral of P sin theta d theta, the limits lower and upper are taken theta 1 and theta 2. This P is taken out of the integration, so integral of dw, that is w, P is out, integral of sin theta d theta, limits theta 1 and theta 2. Now the integration of the sin theta will be equal to minus cos theta, limits theta 1 and theta 2. Substituting the upper and lower limit, so it is minus cos theta 2 plus cos theta 1, and it can be written Pe cos theta 1 minus cos theta 2. This is the work done in rotating the dipole in a uniform electric field.